God bless you. God bless you. All right. Let's get this show on the road here. So, as per usual, we're going to start with questions from homework or whatever else, you know. Bless you. Jeepers creepers.
It's only this class. Not too bad. I'm allergic to math.
That's a bummer. Questions, homework or otherwise. Does anybody have any that we'd like to start with? Delaney. 20. Absolutely. So let's start by looking at the graph and trying to decide whether we think this is... Hey, can we stop the side conversations here? So looking at number 20, I'm going to start by just graphing this and taking a peek to see whether I think this thing is odd or even or neither. If I look here, I notice that the y-axis doesn't quite split it in half. It looks like there's a little bit more on the right side than the left side. You guys see that? Delaney, you buy that? So this, I would say, is neither because it doesn't look quite even to me. Now to show that, remember what we want to show is then that f of negative x does not equal f of x, and f of negative x does not equal negative f of x. Those were the two things that we need to show neither. Oops, I should have written h's though. That's probably unnecessarily confusing, right? Because that's the problem, is all h's in it. Bloop, 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 bloop. Okay. So let's start by doing h of negative x. And we know when we have negative x plugged into a function, what we want to do is we want to replace all the x's in our function with negative x's. So I'll do that. Now, important question. How does negative of negative x squared simplify? What does that simplify down to? It simplifies down to negative x squared. How many negative signs are really there? 3. Right? There's one out front, and then there's 2 because it's negative x squared, right? There's 2 negative x's in there. You just can't see them both. So that's 3 negatives, which makes a negative. And then we have x times x is x squared. Negative x just becomes negative x. And then we have our minus 1. Now we note that this is not equal to h of x, right? Because what was different? We have one sign that's different, but that's enough. So there's our, we're able to say we're not even because of that. Now I'm going to factor off a negative. So if I do that, the negative x squared becomes positive, the negative x becomes positive, and the negative 1 becomes positive. And this is not equal to negative h of x. What are the differences here? Well, my x squared is negative, and my 1 is positive. So again, I can say this is not odd. So if we're not even and we're not odd, we know we are Neither. Does that feel okay? Awesome. Ava. Sure. So 24 asks us to find all the vertical and horizontal asymptotes for the function. So I'm going to start by just graphing this and looking at the picture. So I'm just going to open up my y equals menu. I'm going to type this in exactly as it looks like on my sheet of paper. So remember, to get that horizontal fraction bar, I do alpha, that's the green one, y equals, and then I pick that first option. That's going to allow me to write this in exactly as it looks like on my paper, which is nice. I don't have to muck around with a bunch of fractions or nothing. I'm going to do a zoom standard here. I graph stuff in like every single class I teach, so who knows what my window ever is at the start of any class. So first time through, I always pick zoom standard as opposed to just hitting graph. But for you guys, it's probably just hitting graph is fine, because I don't imagine you're graphing a lot of stuff in your other classes. Maybe you do. Maybe you're sitting there in English class going, oh, how do I graph this essay we're writing? That's a joke. You're clearly not graphing an essay. Come on. Ha 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 ha. No? Okay, fair enough. All right, so if I look at my picture here, I see, let's see, it looks like a vertical asymptote right here. Another vertical asymptote right here. And then a horizontal asymptote right here. You probably typed it in wrong, or your window is different, one or the other.
X over X minus 1.
Okay, x over x minus 1 is number 23.
Oh, shoot.
We're doing 24.
I wonder.
Yep, big difference. Okay, so if I count, looks like 1, 2, 3 to the left, so that looks like x equals negative 3 is a vertical asymptote. And then if I count over here, it looks like 1, 2, 3, and then we got another one. And then it looks like here, just the x-axis appears to be my horizontal. So that is y equals 0 is what that line is. So far, so good. Now I'm going to confirm these with an XY table. So I'm going to start by picking some values that are a little less than negative 3. So maybe negative 3.1, negative 3.01, negative 3.001. And then things that are a little more than negative 3, negative 2.9, and then 2.99, and 2.999. Okay. And I'm just going to take a look at those values. So I'm going to hit vars. I'm going to go over to the y vars. I'm going to choose the function option, and then I'm going to pick y1. And that'll allow me to just tell the calculator to plug negative 3.1 into the function in my y1 spot, which is a heck of a lot quicker than me trying to put negative 3.1 into that equation that we typed in there and having to do that like every time. So I'm going to just press second and enter. After I do that, that'll recall the same thing I typed in, so I don't have to go back through all those menus to get the y1. And I'm just going to update it for my new values. When I look at the stuff left of negative 3, I notice that as I get closer and closer to negative 3, my numbers are getting small, my y's are getting smaller and smaller and smaller. They appear to be growing without bound. That tells me they're heading towards negative infinity. I'll just do the same thing. So second enter, and then I'm going to type in the new stuff. And now this is a little tedious and time consuming, but at least it's not difficult, right? Like once I know how to use my calculator, nothing I'm doing here is like, ooh, scary. Again, if I look at my y's as I'm getting closer and closer to -3 from the right, those values keep getting smaller and smaller and smaller, so I'm going to positive infinity. These two things together tell me that we have a vertical asymptote there. So I feel good about that. Now I'm just going to repeat the same process here for 3. So again, we'll do like something to the left of 3, getting progressively closer to 3. And then something to the right of 3, getting progressively closer and closer to +3. So again, I have -1.53, -16.53, and -166.53. And then we'll just second and enter. I'm going to re-enter these things. Right? Again, this is just a lot of calculating, but I mean, it's relatively easy calculating once you kind of got the feel for it. So what do I got? 180, 1681, 166.81. Again, those are getting smaller without bound. Those are getting bigger without bound. Taken together, tells me I have a vertical asymptote. And then we have the last spot here. Now here I have to be a little bit careful because for the horizontal asymptote, the x aren't approaching a finite value, right? We're looking at what's happening at the far left end and the far right end of our graph. So the x's for a horizontal asymptote are just getting like arbitrarily small or arbitrarily big. So I'll use those values. But at the end of the day, it's like still the same stuff, right? I'm not doing anything cuckoo crazy here. Oh no, I got that stupid decimal again. So the workaround here is I'm going to do, after this, I'm going to press math and then use the decimal command. That'll tell the calculator, give this to me as a decimal. So when I recall this now, I just want to make sure that I don't have to do that asking for a decimal every time. So instead of just like typing over this, I'm going to do second insert and just add a 0 in so it doesn't like overwrite anything. So there's what I got. So -0.31 or 0.132, -0.010, -0.001. Taken together, that looks like it's heading towards 0. And now I'm going to start at the bottom of my table just so I don't have to do all those inserts. So we'll start with the bottom one, and then we'll take 100 and then 10. I just have to remember to write them in the correct spots. Now notice that I did get one weird number there, right? What the heck is 9.98 times, or yada, 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 e -4 mean? See that little e -4 there?
Yeah.
What does that mean? That's just scientific notation. So that's saying that this is 9.98 times 10 to the negative 4. So that's going to be decimal, 3 zeros, and then 998. Right? That's all that's saying. Again, taken together, that looks like that stuff's heading to 0. And since both ends are heading to 0, that tells me that I have that horizontal asymptote at y equals 0. Ava, does that feel good?
Yeah.
Bless you. So again, if you just so you know, like 7.5, and then I have that E there, well, let's just write like times 10 to the negative 15 or something. The calculator does that with that little cap E, right? So all that cap E is just scientific notation. It just means times 10 to the, and then it gives you the exponent. Does everybody remember seeing that maybe in your science class or whatever before? So if those pop up, just keep in mind that that's scientific notation. You got to be careful that it's not 9.98. It's 9.98 times 10 to the negative 4th, which is a really small number, right? Any other homework stuffs? We've done one of each type. Those are good ones to pick because they were, had a lot to do for that last one. At least you had 3 asymptotes to check out, which is kind of a hassle, but like, whatever, we can handle that. Oh my goodness, really?
Sorry.
That's okay. So if I did 23, x over x minus 1. When I look at this, I just see 2 asymptotes. I see one at positive 1, one vertical asymptote here at positive 1, and one horizontal asymptote that also looks like here at positive 1. So set up the same kind of table. My x's I'm going to start left of 1, so maybe 0.9, and then get progressively closer to 1, so 0.99 and 0.999. And we'll just look at after 1, so 1.1, but getting progressively closer, so 1.01 and 1.001. But here, this is a horizontal asymptote, so I'm just worried about getting closer. I'm just worried about like the far left end and far right end of my graph. So negative 10, negative 100, negative 1,000, positive 10, positive 100, positive 1,000. And I'm going to actually start with the horizontal asymptote first here, just because I have it already kind of halfway set up to be doing it on my calculator. I don't have to do a whole lot. So I'm going to start that at negative 1,000. Oops, that was too many. There we go. And then negative 100, and then negative 1,000, or I'm sorry, 10. Oops, forgot to press delete. So we had 0.999, 0.990. Guess I shouldn't have expanded that, and then 0.909. But together, those look like they're heading towards 1, right? Getting a little bit closer each time. Now I'm going to go back. I'm going to snag this one just because it's less inserting. And just kind of do the same thing. So I'm going to start at the bottom and work to the top of my table, just because I don't have to do as many inserts that way. It's a little bit easier. So what do we got here? We have 1.111, 1.010, and then 1.001. Again, taken together, those look like we're heading towards 1. And then here, I don't need that, probably don't need that decimal part anymore, but I'm going to leave it on there just because it doesn't do any harm. And let's go ahead and do the other ones. I'll do my vertical asymptote now. So I have -9, -99, and then -999. Again, looks like we're heading to negative infinity. We're getting smaller without any kind of slowdown. If anything, it's speeding up, right? And we'll do the same thing with the other side. So 1.1, and then 1.01, and then 1.001, $11, 101, 1001. Good. All righty. Let's go and look at 1.7 then. We'll get going on that. So we're going to start here, or section 1.7 is all about function operations. So we're going to start by just looking at how we do basic operations on two functions. So when we say basic operations, we're talking about the standard addition, subtraction, multiplication, division. Yes, of course. So our rules for doing this state as follows. If f and g are two functions with intersecting domains, then for all values of x in the domain, the algebraic operations performed on f and g are defined by the following rules. If I add two functions, or the sum of two functions, I can just take by adding the two individual functions. The difference of two functions can just be the difference of the two individual functions. The product of two functions is just the product of the two individual functions. And the quotient of two functions is just the quotient of the individual functions, assuming that the denominator is non-zero. Yes. We've already done one, right? There'll be a test soonish, sure. I don't have it scheduled yet because we haven't even, like we're still in 1.7 and this is usually at least a 1-day unit or section or whatever. So, end of next week or the following, not sure. I don't know. Okay. So what does this mean for us? Well, we can use it to do problems like the following. Drop those in. Bloop. So let's look. Here we're asked to do the sum of f, or we're doing f plus g of x. What does that tell me? Well, if I use my rule from above, that tells me I can just do f of x plus g of x. And I know from my definition here in the problem that f of x is 2x minus 3, and g of x is the square root of x plus 2. So I'll just replace my f and g with the appropriate function. So far, so good. And then all that's left is to potentially combine any like terms, do any kind of simplifying I might be able to do. Since the only operations going on here are like addition and subtraction, is there any like terms to combine? What do you guys see? Anything? No, right? The 2x and the 3 can't combine because they're not like terms. One has an x, the other doesn't. The stuff that's underneath the radical I know can't combine with stuff outside of a radical. So there's really nothing else to do here. So that's done. Let's see, we have g minus f of x. So I know I can just do g of x minus f of x. And I'll just replace that stuff with what it's equal to. So I'll just write this, correct? Does that look good to everybody? Nobody disagrees? Because it's not right. Oh no. Mr. Kulik made a mistake. He did it on purpose. Does anybody see the mistake? Okay, let me show you then. So here it says all of f of x is negative. So I should have a parenthesis here because I'm going to have to then distribute that negative through. So really what I should have written would be square root x plus 2 minus 2x plus 3. Well, just for emphasis, you know. Now that I've shown you that trick, I'm going to try to use it on you again. As a fair warning, I am going to try to use that trick on you again, so be prepared. Okay. I know. So here we have g times g of x. Again, from my rules above, I know that's just the same thing as g of x times g of x.
Can you yell at them?
And in the problem, it tells me that g of x is just equal to square root x plus 2 okay. So far, so good. Sid, you were shaking your head. Is it not okay? It's okay? Okay. If you're stuck, say something, right? It's okay. Ava? Why aren't we using the twos? Well, those were the F and G that were given in the problem.
Oh.
Right? So I'm just using what it told me, right? The problem will tell you something, that F is something and G is something. Those are the F and G for this one. They could be anything. All right. So in the next step, we've done the hard part, right? We just have to now see if there's any simplification I can do. Can I do any simplifying here? Yes is the correct answer. What can I do? Well, I didn't hear because you're both kind of doing it at the same time and I'm mumbling between the two of you. Okay, what would you tell me to write then?
Would you multiply them?
Okay. I mean, you do multiply them. And how would you write it after you've done the multiplication? Sure. Let me ask you a different question. If I just had y times y, what would you write?
Y squared.
Y squared.
So is it x squared plus 2 squared?
It would not be that. Would not be that.
Oh, yeah.
X plus 2 squared.
Oh.
Don't they just cancel out though?
And now, correct, so Bladen says that the squared and the square root do cancel each other out.
So it's just x plus 2.
So, Sid, when you started to say the square root goes away, I just wanted to hear like where that was heading, because potentially you had the right answer there. I just wasn't sure what you meant.
Yeah.
You took her down the wrong path.
Yeah. No, I'm saying, yeah.
That's everybody's okay though. We kind of remember that. It's about looking at it the right way, correct?
Yeah.
It just can be sneaky sometimes. All right, let's see. What do we have next? We have f divided by g of x. So again, we'll write f of x over g of x. And we know that f of x is 2x minus 3. And g of x is x plus, or square root of x plus 2. Is everybody okay here? Next step would be to simplify this. Is there any simplifying I want to do? Well, think back to geometry. Do you remember any rule in geometry about fractions with square roots in them? Right. So in geometry, we said we didn't want to leave square roots in the denominator of our fraction, right? Hold on. Yeah, you're doing fine. I just want to slow down though, okay? That's okay. You're fine. I love that we're participating. Like, don't let me frustrate you. Come on in. Hi, Miss Mahoney. You're fine. Nora, it's for you. So in geometry, we said we didn't want to leave any fractions with a radical in the denominator, correct? We see a radical in the denominator in this problem. But what is different from the way this radical looks than the radicals we saw in geometry? It has an x in it also, right? right? It's the square root of a polynomial in this case, rather than just like the square root of a number down there. Here's the deal I'm going to make with you guys. Still expect you to rationalize denominators. Get rid of the square roots in the denominator if it's just a number under the square root. If it's an expression with a variable in it, just leave it the way it is. So we'll just leave this one the way it is. I want to acknowledge that we have had that rule in the past, but we're going to abridge that rule for this course because we're going to see things where there's an expression with a square root in it, and you can just leave that be. But if it's a number, that we're going to take care of. Everybody cool with that plan? Seems fair enough. There is a fifth operation that we can do on two functions. So we have addition, subtraction, multiplication, division. What do we guess that the fifth operation is that we can do on functions? You did it last year in Algebra 2. Is that a hand, Paulie?
Oh, yeah, exactly.
Sure. I'll give you a hint. It starts with the letter C.
Yeah, T.
Yeah, we're going to talk now about a fifth operation that we can do on two functions. This is something you talked about last year in Algebra 2. This fifth operation starts with the letter C. Does anybody remember what that would have been? Not corresponding. That is a word. What? Not constant. Although those are both math words. Or continuous. It is composition.
That's not a word.
That is a word. So if we let f and g be two functions such that the domain of f intersects the range of g, the composition f of g, which we denote with this symbol. So when we read that as f of g, or f compose g, is defined as f of g of x. Does that symbol look familiar now?
Oh, yeah. The little circle.
The little circle, that's composition.
I remember
Right.
this, actually.
Good.
It's like a vague memory in the back of my head.
Yeah,
Can I go a little about?
sure. No
Why is it
problem.
icicles though?
Yeah, every classroom is free.
I'm pulling my socks.
I mean, I have the temperature set at 71, which seems really reasonably appropriate,
Yeah,
but
this is cold in the school.
I think it's because it's been cold outside. If it was 80 degrees outside and it's just set at 71, you'd be like, oh, this is fine.
Yeah.
I think it's because it's cold outside. All right. So let's do some examples. Okay. So we have two functions. Our f of x is the function 2x squared minus 3x. And our g of x is the function negative 3x plus 4. And we're going to do these three compositions. Can Mr. Kulik state for the record a pet peeve of his? When you read this symbol, if you say fog, I'm going to lose my stuff.
Fog.
Yeah.
Now I see it.
Yeah, don't say that, please, for the love of God. Say F compose G. It just makes you sound like
I forget what the circle means.
it means compose. That's what you read it as, is compose. I know it looks like the word fog. Please don't say that. It just makes you sound like you haven't been paying attention for the last month. And it's like, oh boy, we're doing that, huh? Okay. So, using our definition of composition above, I will rewrite this as f of g of x. So far, so good. from the problem, we're told that g of x is negative 3x plus 4. So I'll replace the g of x with what it's equal to, that being negative 3x plus 4. Now, what does it mean when I have a function and then the parentheses with stuff inside of it? What am I supposed to do with that stuff inside of it? Plug it into the x's, right? So everywhere in f where I had an x, I'm going to replace that x with negative 3x plus 4. So where I had my x, I'm just going to have now negative 3x plus 4. So far, so good?
Great. Splendid.
Okay.
I thought it was the other way. It's not the other way.
It's not the other way. Yes. Sure. What do I need to do next?
Solve.
Well, not solve, because it doesn't, we don't have it equal to something. We mean the other S word, simplify.
Sure.
Okay? What should I do first to simplify this?
Distribute the 2 times -3x.
Definitely not that, because you're violating the order of operations. We should do the exponent first, right?
I didn't see it.
Yep. How do I do negative 3x plus 4 to the second?
Just do it.
Just do it. Anybody with a more detail than just do it?
Doesn't seem tough.
Did not seem to. Okay, what does it mean when I have something squared? Like if I have x squared, what does that mean? X times x, right? Everybody agree with that? So if I have negative 3x plus 4 squared, it really means this, right? Everybody agree there?
It's all right.
Okay. What should I do now?
Distribute. No,
Just
wait.
okay, wait.
Foil.
Okay. So it's a great question. Should we distribute first or should we FOIL first?
Parentheses.
Here's the answer. Doesn't matter.
What the heck?
But my recommendation to you is to FOIL first. Because the most common mistake you're going to make when distributing is to try to put that 2 into both sets of parentheses rather than just one. So let's just FOIL this. So I still have that 2 out front. Negative 3x times negative 3x is
9x
squared.
squared.
Negative 3x times 4 is
Negative 12x.
4 times negative 3x. And then 4 times 4.
16.
And let's go ahead and do this at the same time, right? Because we're going to need to do that eventually.
X plus negative 12.
Everybody's so far so good? Okay. Notice inside this parentheses we can combine the 12x's to make negative, or the negative 12x's to make negative 24x. And now if we combine like terms, these guys can combine together and those guys can combine together, correct? And we're done.
So we're not going down.
Try to factor that. You could if you wanted to. It's no more correct. It would be no more correct than it is right now, though. Ava. Absolutely. So if you wanted to, you could keep going and try to. Yeah, I mean, I'm just letting you know it's not wrong to do that, but it's not going to be any more simplified.
Yeah, we just spent a bunch doing it.
Yeah, and in fact, I'm pretty sure by looking at the added, it's not going to be factorable. So, all right, let's do B. Oh my gosh, Mr. Kulik, are they all this long?
That's what I'm saying.
Well, if we look at this, the composition ended here, right?
Yeah,
The hard part was just all the simplifying afterwards.
yeah.
So a lot of it's just going to depend on the expression that we have and how difficult it is to simplify. Sometimes it might be really easy to simplify. They might not all be that bad. So we'll start. G compose f of x is just equal to g of f of x. And we know from the problem, f of x is 2x squared minus 3x. So if I want to do g of 2x squared minus 3x, everywhere in g I had an x, I'm going to replace with 2x squared minus 3x. So I still have my negative 3, then I have my 2x squared minus 3x, and then I have my plus 4. Everybody okay here? Now we simplify. What do I need to do to simplify this?
Just distribute.
Yeah, just distribute that negative 3, right? And we're done. Oh boy, that was a lot easier than the previous one, wasn't it? So it just kind of depends on, you know, like what f and g are and the simplifying you're left with. Sometimes it's really quick. Sometimes it's not so quick. And it's maybe not entirely clear until you like get into the problem which one it's going to kind of be. Let's look at C. Ooh, Mr. Kulik, F compose F. So what would that mean? That would mean F of X. So F of X, remember, was 2x squared minus 3x. And we're going to be plugging that into the x's in f of x. Oh, no, Mr. Kulik, this looks bad. Well, it kind of is. It ain't great. Not great, Bob. Oh, no! So what are we going to have to do here?
We're gonna foil.
Yeah, we have to foil again, right? In the interest of already looking like I'm boring you guys to tears, I'm going to do this foiling quickly in my head. Sound okay to you guys?
Sounds good.
12. And then you can go and ask Mr. Kulik, how did you do that, like in your head, without writing anything down? And I would say, okay, well, in Algebra 2, you would have talked about these perfect square factoring patterns. Does that look like something you talked about? Sure.
Yeah.
Well, I'm using that pattern here, so I just did like a squared minus 2ab, so 2x squared times negative 3x times 2. That was my 12, x cubed. And then b squared, which is just negative 3x squared, so 9x squared. It allowed me to do it quickly in my head because I remembered that formula. If you didn't, that's fine. We could FOIL also, which is what I wrote there. All right. Now we just do a little bit of distributing and some combining of like terms, and that ought to do it for us. So there's only one pair of like terms, that's the x squareds. There you go. Now I sped through that a little bit because I shortcutted the foiling, right? But again, it's just foiling. You've done it, I don't know, probably 3 years, pre-algebra, algebra, algebra 2. So hopefully we're pretty good at that. Okay. All right. So one of the nice things about composition of two functions is it lends us nicely to talking about inverses. So in fact, we'll use the composition of two functions as our algebraic definition for what we mean of an inverse. So we say let f and g be two functions, and we say that g is the inverse function of f, provided that f compose g of x is equal to g compose f of x, which is all equal to x. If that's the case, we say that the function g of x can be written as f with this negative 1 exponent on it of x, which we read as f inverse, or we can read it as the inverse of f. Keep in mind that this here does not mean like 1 over f of x, right? That negative 1 in the exponent is part of the name. It's not an actual exponent. So it's just read as f inverse. So that's the algebraic definition. But what is this really saying, right? So let's go back to our functions. So like if we have some function f, its inverse should be some function that, let me draw it this way. That'll take that y and send it back to x. Right? So we're saying that if f of x1 gives me y1, then f inverse of y1 has to give me back x1. It has to be our map back to where we started. So what happens when we do the composition? If I do f of f inverse of, let's write it the other way. If I do f inverse of f of x1, well, f of x1 just sends it to y1, And f inverse of y1 sends us back to x1. And what have we done? We're just back to where we started. We've done nothing at all, right? So that's the idea of what we want these inverses to do, to just basically cancel each other out, or to undo what it is that the function was doing. So f inverse should just kind of undo whatever f was doing. Let's look at some examples here. We'll start off with functions that are not, or like the, some of these less used function or ways to represent a function. So let's take a look at this mapping diagram. What is the inverse for this mapping diagram going to look like? What value should be in my domain? Great. And what value should be in my range? 1, 2, 3. And what should 4 go to? Back to 1. And 5 should go to 3. And 6 should go to 2. And we'll call that guy f inverse. Done. Woo! This is so hard. No, man. That was a piece of cake, right? NBD. Notice, is f inverse a function? Yes, right? Every domain is used, and each domain only goes to one location, right? Let's look at another example. So here is my function f of x represented by the set of ordered pairs -2, 4, -1, 6, 3, 8, and 5, 8. What would my inverse look like as a set of ordered pairs? Good. Great. What? 8, 3, and 8, 5. Perfect. Is this a function? Why not? Yeah, I have an x coordinate used more than once. So right away I'm going to notice that, hey, not every inverse is going to be a function. Good, okay. At some point, we would like to be able to predict kind of when that's going to happen, but we're not quite ready to talk. Oh, I guess we are going to talk about that right next. Okay. So let's talk about domains and ranges here for functions and their inverses. So remind yourself here that the domain is the set of inputs and the range is the set of outputs. If we go back to these previous problems, if I look at f, the domain here is the numbers 1, 2, and 3. And the range is the numbers 4, 5, and 6. If I look at f inverse, the domain is the numbers 4, 5, 6. And the range is the numbers 1, 2, 3. What do we notice there, the relationship between f and f inverse and their domains and ranges? That the domain of f is the range of f inverse. And the range of F is the domain of F inverse. Everybody see that? Let's check down here if that still holds. So for F, our domain is -2, -1, 3, and 5, just the x's. And the range is 4, 6, 8, and 8 again, but I know I don't ever repeat elements in a set, so we're just going to write that once. For F inverse, our domain was 4, 6, 8, and then 8 again, but we only write things in a set one time. And the range was -2, -1, 3, and 5. And again, I see the same thing going on, right? The domain from F is the range for F inverse. The range for F is the domain for F inverse. Okay. So what I want to do next is I'm going to introduce two new terms that we use to, actually 3 new terms that we're going to use as additional function descriptors. So again, these 3 terms are attributes used to describe some characteristic of a function. I'm going to put them all in at once. And then we're going to talk about them. So the first term is called onto, or some textbooks would call this surjective. And we say a function is considered onto if every element in the range is mapped to by some element from the domain. In other words, no element in the range remains unused. Everybody's okay with that idea? The next term, a function is considered one-to-one, or some textbooks call that injective, if every element in the domain maps uniquely to distinct elements in the range. In other words, no element in the range is used by multiple elements of the domain. So no range could be used more than once. And our last term is bijective. It says that a function that is both onto and one-to-one is called bijective. In other words, if you're both one-to-one and onto, every element in the domain is used one time, and every element in the range is used one time. So let's take a look at an example here. So let's look at, actually before we do this one, let's go back. Let's look at this graph here. If I look at F, we said F was a function, right? Is F onto? Is F onto? All I'm going to do is look at the range. Are all the ranges used? Then F is onto. Is F one-to-one? Yes. Why? Because each range is used by exactly one domain. What can we say then about F? Good. Let's go and look at this F down here in example 14. Is F onto? Sure, right? It's got some values, uses them, but is it one-to-one? No. It's not one-to-one because we have a repeated y coordinate. Okay. Notice here that since F was not one-to-one, F inverse failed to be a function, right? And why did it fail? We had some repeated x's, right? So the repeated outputs in F become repeated inputs in F inverse. Everybody's okay with that? Okay. Let's look at this example. It says, given the function f of x in the graph below, find the graph of the inverse of f. So what I would do is I know that f inverse should have the points 5, -2, -1, comma 1, and -3, comma 0. So I'm going to go ahead and plot those. 1, 2, 3. So there's -3, comma 0. There's -1, 1. There's 1, 2, 3, 4, 5. 1, 2, 5, -2. Now, I know that the vertex in F should still be the vertex in F inverse. So that kind of tells me how to draw this. Is everybody okay there? Notice is F inverse a function? No, why not? Fails the vertical line test. Excellent. Now you might also remember from your Algebra 2 class, if we plot the line y equals x, we notice that f and f inverse are reflections of each other across that line, y equals x. Right, so if I look at like this part of f becomes, when I reflect it across that line, y equals x becomes like that part of f inverse. You kind of see that? Maybe. So notice here again that was, if we go back and look at F here, is F 1-to-1? No, why not? Well, if I look, let's say this point here. What's the coordinate at that point? And if we look at the y coordinate here, we have a repeated y coordinate, right? So how might we easily check to see if a graph represents a function that's one-to-one? So if we can draw a horizontal line where that intersects the graph more than once, then f can't be one-to-one, right? Because that would imply it has a repeated y coordinate, correct? So we'll call this the horizontal line test. We'll say that the horizontal line test defines y as a one-to-one function of x if and only if there is no horizontal line that intersects the graph at more than one point. Furthermore, what can we say then about a horizontal line test? It tells us if that a function is not one-to-one, and if f is not one-to-one, that would tell us that f inverse is not a function, right? So what can we say about the horizontal line test? In addition to telling us about f, it can also tell us about f inverse, right? Is this ringing any bells from Algebra 2? I think you talk about this stuff in Algebra 2 as well. Maybe not. You would have done it in the beginning of the year, so if you've forgotten by now. Or you just had 3 Algebra 2 teachers last year, and it's like, yo, we did some stuff, but it was kind of a mess, and I don't really remember. You know, like I get it. So we've looked at how to find inverses if you're given a mapping diagram, right? That was easy. We've looked at finding inverses if you're given a set of ordered pairs. That was pretty easy. We looked at finding inverse if you're given a graph. Again, that wasn't too bad. What representation for a function haven't we done this for yet? Equation. So let's look at finding the inverse for an equation. Yeah, this will be the last thing that we do. This example, we have a ton of examples after this because it's not trivial, this process, because the algebra can be kind of hairy. And it gives me a good opportunity to review like a lot of algebra stuff you would have seen in Algebra 2 that may not be like right at the top of your head. All right. So first thing I'm going to do is I'm going to rewrite my f of x as a y. And now I'm going to rearrange this equation to get x by itself. So this will be the same steps regardless. So we rewrite with a y. We rearrange the equation to get the x by itself. Okay, and then my last step is to rewrite this equation where I've swapped the x's and y's. So everywhere there's a y, I'm going to write an x. And everywhere there's an x, I'm going to write a y. Or I could just write this at this point now, and I could say like f inverse of x equals this. Now for a linear equation, this is pretty trivial. we're going to look at some other examples further on where this becomes much less trivial. At this point, you guys should be able to start this stuff. And here's the bad news. This runs all the way from 25 to 56. But nothing is due this weekend, right? Or this part is not due this weekend. Okay? Just 19 through 24. And hold on, guys. Hold on. I have a Delta Math assignment that I made. So this Delta Math assignment has 6 problem types. You have to do 4 correct in each one. There's no penalty for wrong answers. It doesn't mean you need to get 4 in a row correct. It just means eventually you have to get 4 correct. That should be due by Sunday also.
Next Sunday or this Sunday?
This Sunday. But everything in there is stuff that you can do pretty easily. Shouldn't be anything in here that's super duper difficult. Okay? And you guys can go to lunch. You too.